Part 5, Gestalt theory. Gestalt theory is a holistic field-like principle of computation that defies explanation in conventional computational terms. The principles of emergence, reification, multistability, and invariance are prominent aspects of visual function. Emergence is seen here in this dog picture, known well in vision circles as a picture of a Dalmation dog under the shade of overhanging trees with its tail up in the air here somewhere. You can see that this picture emerges spontaneously from the coincidental alignment of innumerable local edges that suggest three-dimensional surfaces. You can actually see the surface of the dog's back by an emergent principle. Reification we have already seen in the case of these visual illusions. Multistability, there are percepts that can pop back and forth between two alternative interpretations, suggesting that the perceptual system is itself multistable. And invariance is the ability to recognize shapes invariant to factors such as their rotation, their translation, and their scaling by perspective. These shapes in A here are easily distinguished from these shapes in B, even though they're composed of the same elemental components, and they are still recognized through various different distortions, including perspective distortions and morphological transformations, and even despite expressing the shapes in different perceptual primitives. Wolfgang Köhler, in his book on Die physische Gestalten, describes systems that exhibit Gestalt emergence, showing that there's no magic in emergence. There are certain kinds of systems that have emergence. For example, water seeking its own level. How does the water know exactly what level to appear in each tube? Well, it's a matter of every particle of water pushing on every other particle all at the same time, and they're all moving at the same time until they reach an equilibrium. Emergence is also seen in the distribution of electric charge on a conductor, where the charge distributes itself more densely at high curvature points and less densely at low curvature points, and it instantly re-equilibrates whenever additional charges are added. The soap bubble is also used an example of Gestalt emergence, where the spherical shape of the soap bubble is not defined in any mathematical formula or template, but rather it emerges by the simultaneous parallel action of every part of the surface pulling on every other part simultaneously. And emergence is seen in the phenomena of waves and resonance. Indeed, I propose that harmonic resonance is the ultimate Gestalt phenomenon, exhibiting as it does all of the Gestalt properties of emergence, reification, multistability, and invariance. Now, a word about paradigms of computation. We're all familiar with the analog paradigm, where you have analog electronics working on analog signals, and digital, as in modern computers, where we have digital components connected, processing digital square wave type signals. Both of these paradigms exhibit discrete computational elements connected by discrete wires in a circuit network. I'd like to introduce a different paradigm of computation, the spatial computational paradigm, which involves spatial computation across a spatial medium. For example, the game of life is a spatial computational algorithm. The algorithm depends on the spatial arrangement of the pixels, and the interactions between the pixels are spatial interactions. This is, of course, a digital form of a spatial computation. Here's an analog principle of computation in the Grassfire algorithm. This is an algorithm used in image processing to compute the medial axis skeletons of various geometrical shapes. So for instance, for this rectangle, we ignite a Grassfire, metaphorically, around the perimeter of the field, and then we track the flame fronts as they advance in towards the center of the figure. at points where two flame fronts meet, or along the center where opposite flame fronts meet, you mark the central axis skeleton. So this is, again, a spatial computation across a spatial medium. Again, it can be computed in digital on a digital computer, but the algorithm must perform as if it was performing on a spatial field. The most impressive spatial computation is seen in the optical Fourier transform that is performed by a simple lens. And if you take an input image like a photographic slide, in this case of a sinusoidal grating, and you place it at one focal length of the lens, and over on the other focal length you place a frosted glass screen, and if you illuminated the input image with coherent light, like a collimated laser beam, then this lens performs a Fourier transform on this image. And it's all done by analog computation, waves passing through the lens and intersecting and overlapping. And remarkably, this mechanism also does the inverse Fourier transform. The glowing of these three spots is inverse transformed into a sinusoidal grating again. And ripples on a pond can be seen as an analog computational mechanism. It may not actually represent anything beyond itself, just the waves, but ripple tanks are often used to demonstrate optical phenomena, and therefore the ripples on a pond are a spatial computational medium that follows certain spatial laws. And perhaps the most impressive example is the principle of phase conjugation, where laser beams crossing in space create interference patterns. Now, if these two laser beams cross in space, this is the kind of interference pattern that they create that lines up with the angular bisector, the angle between the two beams. Now, if this intersection takes place within the solid volume of a transparent nonlinear optical material, and just about any glass goes nonlinear if the amplitude gets high enough, then this pattern of diffraction actually warps the glass in the same pattern as the diffraction. And this means that when other beams are sent in here, for example, this is the same situation we have over here. We have beam 1 coming in from here, beam 2 coming in from here, and now we get a probe beam, and it can come in from any direction you like, but if it comes in and it hits that zone of intersection, it reflects and refracts off the interference pattern and makes a reflected signal beam coming out this side. A wave vector diagram can predict how these things go. Starting from the origin, the beam 1 makes a wave vector k1, and then beam 2 makes the wave vector k2. So this point in the diagram is the position of k1 plus k2. Now you send in the probe beam coming in from here, that's k3, and the wave vector diagram will be closed by k4 that goes from the last point back to the origin again. It always has to go back to the origin, and this completion of the circle into the origin is what produces the reification in phase conjugation. So in order to produce a phase conjugate mirror, all you have to do is take the probe beams, beam 1 and beam 2, and point them at each other, anti-parallel to each other, and they will create a standing wave inside this area of inside this tube. And now the probe beam comes in over here from whatever angle it chooses to come in from, and from the wave vector diagram, the K1 and K2 cancel each other out. So when K3 comes in, it must create a K4 to close the wave vector diagram, and K4 is the phase conjugate beam. It's the time reversed beam that turns the incoming beam 3 into a standing wave as it mixes with the outgoing wave B4. So how does this work? In a regular mirror, an incident ray is reflected off the surface and comes back out the same way that it came in. In a phase conjugate mirror, similar behavior is observed, that it reflects off the volume of interference patterns inside here and goes back out the way it came. Now, when the light comes in at an angle, where the angle of incidence equals the angle of reflection, the phase conjugate mirror does something different. It goes reflected back out again, reversing the incoming ray. And this has some rather interesting properties. For example, if you have a coherent beam of light or some kind of image, and you send it through a distorting glass, wavy kind of bathroom glass, then it distorts the image. And when you reflect the reflection of the image, it will go back through the distorter on a second pass and get even more distorted. In a phase conjugate mirror, something very strange happens, that the distorting glass does indeed distort the incoming beam, but then the reflection traces back the distorted beams right through the distorting glass and undistorts them again. This can be done with amplification. This is a remarkable wave-like computation which has direct significance for the brain. Part 6. Properties of harmonic resonance.